In this example problem, we want to know if the mass of the Sun were to double, what would be the orbital period of the Earth around the Sun? So remember, the Sun exerts a gravitational force on the Earth. So we're looking at the idea that the gravitational force from the Sun is going to change. And so when we sum forces in the radial direction, we find that the mass is directly proportional to the orbital velocity squared. So if we change the mass of the Sun, remember this mass here is big M, or the one that's at the center of motion, and this velocity over here is the orbital speed. So if this mass changes, this variable here will change as well. And remember, we use this relationship here in order to derive Kepler's third law over here. So we have, rather than going through the derivation again, we can look at our equation sheet and see how orbital period relates to the mass that is being orbited. So I looked up the distance between the Earth and the Sun, because the problem does not state that that changes, the gravitational constant, and then I looked at the mass of the Sun, and I'm multiplying it by 2 here. So when we take 4 pi squared times 1.496 times 10^11 meters cubed, and then we would divide that by 6.67 times 10 to the minus 11 newton meters squared per kilogram squared, so that gravitational constant, times 2 times the mass of the Sun, 1.99 times 10 to the 30 kilograms. When we rearrange that, we get that the period is equal to 2.23 times 10 to the 7 seconds. So Kepler's third law does produce a period in seconds, but our brain does not typically think in that many seconds. So I converted this to years. So you'll see that the orbital period of the Earth will decrease if you increase the mass of the Sun, which makes sense because mass is proportional to velocity squared, so you expect to see the orbital speed to increase and therefore the period to decrease, since it's covering the same distance in a faster rate, so a shorter time.